Okay.
Yeah.
So, hello, my name is Lewi Uberg. I am an applied data science graduate and a full stack developer in Norway. I chose analysis of brain tumor using MRI images for my degree project, supervised by Dr. Seifedine Kadry. There is an increasing death rate caused by brain tumors in humans. Therefore, diagnosis and treatment of brain tumors correspondingly increase the need for medical personnel. Such personnel is in high demand, and time is of the essence with brain tumors. To reduce the workload and time from suspicion to diagnosis, this project seems to automate the initial part of the process by implementing a computer-aided diagnosis system to classify low-grade and high-grade gliomas automatically. The goal is to start by studying several types of brain tumors and how they are classified, how convolutional neural networks function to better understand how to implement and manipulate them. I then looked at several pre-trained architectures to take advantage of transfer learning, but I didn't spend too much time looking for data sources initially, thinking it would be a small task with the abundance of data on the internet today. While the main goal is to train a model with high success rate, I wanted to present something more than a Python script or an interactive notebook. Therefore, I am making a website where the user can upload a brain tumor MRI and get the predictions returned by all the models. The World Health Organization tissue classification system categorizes glicomas in 4 levels, from benign to most malignant and recurrence prone. Low-grade gliomas consist of grade 1 and 2 tumors, while high-grade gliomas consist of 3 and 4. Low-grade gliomas generally have a good prognosis and prolonged survival rate, but only account for 25% of gliomas. The remaining 75% are high-grade gliomas, with 56% being the most common and aggressive glioblastoma multiforme. High-grade gliomas, particularly GMB, have a grim prognosis with a median survival of 15 months. Despite the best available treatments, the gold standard for diagnosis and grading brain tumors is with an examination of the tissue. But this surgical resection is risky and invasive. However, MRI scans are non-invasive and currently produce the procedure of choice for identifying tumors. The concept of convolutional neural networks was introduced in 1980 to model the brain's visual cortex. It is one of the most successful pattern recognition models and most commonly used for image pattern detection. The typical starting point when designing a CNN is with the LeNet 5 architecture. As the name suggests, it's 5 layers deep, 2 convolutional layers, 3 fully connected layers. Unfortunately, being a breakthrough, when introduced, LeNet is shallow and lacks the complexity to allow it to generalize well. Put in other terms, it does not perform well on new data. Over the years, CNN architectures have evolved by adding the ReLU activation function, dropout method, batch normalization, and so on. But the most evident change is stacking more fully connected layers on the model to increase the depth and complexity. However, greater depth increases the vanishing grading problem. In other words, it makes the model overfit on the data. Inception nets use small parallel networks inside the main network to combat this problem, while ResNet uses skip connections to achieve the same result. And DenseNet's approach to solving the problem is to directly connect all the layers with matching feature map sizes. Before implementing any classification models, I needed to gather the data. I expected to use very little time on this, since it looked like there was plenty of usable data sets on places like Kaggle. However, I was very wrong. Most data sets I found were too small, didn't have the tumor types I based my previous work on, or in some cases, when I cleaned the data for missing values and error, there wasn't much left. After spending much time searching, I remembered a paper I didn't include in my proposal since I found it right before submission. This paper used the Rembrandt dataset, which looked to fit my needs. Unfortunately, the accompanying information of the images was spread over many files, and the MRI images were in the DICOM file format, which has a lot of metadata built in and is awkward to work with. After spending much time combining and cleaning this data, I have the same results and sample values as described in the paper. However, I could not find where it was given if the MRI slide was tumorous or not. I found that only on the patient level. Without this information, the dataset was useless because the label I found would mark all the patient slides as tumorous, while in reality, it's just present in about 20% of the slides. I used every night for weeks looking for the key without luck. So my supervisor and I reached out to the paper's main author, and he agreed to a meeting some weeks later. He had some terrible news. The information I needed was not in the dataset. He had employed radiologists to classify each slide manually. He was kind enough to offer me to share this data with me, and a couple of weeks later, I received the dataset. It was much smaller than in his paper, but still something to work with. I cleaned the data for errors and duplicates, and I made functions and for data augmentation. These functions made a copy of the image, mirrored it, made another copy, rotated it, and so on. Basically enlarging the number of pictures. I made it so I could turn this on and off to see the impact on the model. After using about 10 hours, 10 times the time I planned, I could finally move on. I used the Teras and the TensorFlow Keras framework to implement VGG16, MobileNet, ResNext, DenseNet 121, and my own custom model. The easiest to implement was my own, which was a very basic architecture, but I added the feature I found in my research that my intuition said would be impactful. Another reason that my custom model does not use transfer learning like the other models. Transfer learning uses pre-trained weights from general datasets like ImageNet for all, but the last few fully connected layers. In other words, it uses previously learned general knowledge and only trains project-specific details in the last step. Since I knew from previous work that there would be a lot of fine-tuning and that I was probably going to run hundreds of tests on all the networks, I invested a great deal of time developing a pipeline that would let me swap out the architecture and turn the dials as I liked during experimentation. Since my dataset was a little smaller than I would prefer, I used much time running tests to find the best split on train validation and test sets. My final decision was to extract 20 random slides from each of the 3 classes for testing and verification. Then I split the remaining to give me a 70% for training and 30% for validation. When starting the main model training, it became clear that doing this tremendous amount of testing had made me find the optimal hyperparameter settings as well. So even though I got really good results after only a couple of runs, I trained the models many times to verify that it wasn't just luck. As I said, I got some outstanding results, in some cases better than any I've seen for MRI classifications. I suspect my results might go down a little if I were to add more samples to the test set. But to do that, I would have to get slides manually classified, which the time frame of my project wasn't, I couldn't permit that amount of time. Still, I'm happy with the results and a little surprised. My custom model consistently ranked second, only beaten by DenseNet. The best results of each model all got better results than the paper I used the same data set as. And the top two models had a perfect accuracy and F1 score, even with the added samples. And I am confident that these models will perform well. The reason that even though augmenting the data yielded a little better results, it was not as significant as I would have imagined, positive or negative. An observation was made due to a small error in the code. In some of the tests, the pre-trained weights weren't loaded, and loading them didn't affect the results too much either. The project may be so narrow that this general knowledge is insignificant. The custom model certainly suggests so. The next logical step and most important step for this project is to add more labeled images. Still, it needs a practical application. Therefore, in parallel, a website is being developed where the user uploads an image and gets the classification results from one or more models in return. The API in development lets the user get the results directly in the terminal using curl commands, but a front end is also implemented for convenience. Thank you very much.
Thank you very much for an interesting presentation and very important from the practical point of view. So now we still have time for maybe one or two questions. So please go ahead. If not, I have a very short and maybe not so relevant question. I mean, I understand this is an area of medical applications, but did you think about using some kind of data augmentation? I understand that certain regions of the tumor are so specific that you can easily move them to other areas and then get something like another artificial case of a brain tumor. So is it possible in this area, or it's just a very bad idea?
You can do it, but you have to be very careful. So you can do rotations and flips and stuff like that, mirroring, but you shouldn't like skew or to make more images. You can zoom and you can rotate it a bit, but skewing and distorting the colors and stuff like that wouldn't give good general results.
Okay, thank you very much.
So the website is complete and will be on tumorclass.info very soon.
Thank you.